Hello everyone, welcome back to another Biopharmaceutics and Pharmacokinetic video. Today we'll be discussing the one compartment open model, specifically for extravascular administration. Let's break this down in the simplest way possible. First things first, when a drug is given by an extravascular route like oral, subcutaneous, intramuscular, absorption becomes must before the drug can reach systemic circulation and shows its therapeutic effect or activity. So basically, before a drug can work, it needs to be absorbed into the bloodstream. Now the rate of absorption can happen in two ways: zero order absorption or the first order absorption. Talking about the zero order absorption, the drug is absorbed at a constant rate, like water dripping from a tap at a fixed rate. It does not depend on how much drug is left to be absorbed. Example, some controlled release dosage forms. Next we have is first order absorption. The rate decreases over time in first order absorption. It depends on how much of the drug is still left at the absorption site, and the first order absorption is followed by most of the drugs given orally. So they follow this model only. Let's look at the basic equation for drug concentration over time. So net change in plasma drug level will be the rate of absorption minus rate of elimination. In this case, in extravascular administration, we will be having the absorption rate, which is represented as EV or A, and the elimination, which is represented by XE, elimination rate constant. Now look at the graph plots. In a regular Cartesian plot, you will see a curve, but in semi-log plot, the first order process becomes straight line. It is very useful for estimating drug constants. After a single dose of an extravascular drug, the plasma drug concentration time curve can be divided into four main phases. First one is absorption phase, then plateau phase, followed by post-absorption phase, and lastly we have the elimination phase. Talking about the absorption phase, at time 0, okay, at time 0 the entire dose is present at the absorption site. So during this phase, absorption rate is more than elimination rate. Okay, absorption rate will be more when compared to elimination rate because the absorption site has the entire dose. So the plasma concentration starts rising gradually. Now we have the plateau phase. At peak time, this plateau phase will occur. This is a short moment when the rate of absorption equals to the rate of elimination. Okay, the rate of absorption will be equal to the rate of elimination. The plasma drug concentration reaches its maximum Cmax. Okay, Cmax at time Tmax. So mathematically, this is when dxa divided by dt equals to dxc divided by dt. So net will be the 0 because rate of absorption is equal to rate of elimination. So net rate will be the 0. But remember, this phase does not last long. Now we have a post absorption phase. The rate of elimination in this phase exceeds the rate of absorption. So the drug is still being absorbed but in smaller amounts. the plasma concentration starts declining slowly. Let's move on to elimination phase. Finally, when there is almost no drug left at the absorption site, the rate of absorption approaches zero. Okay, zero. The decline in plasma concentration is governed by only dependent by entirely elimination. This phase follows first order kinetics and it is represented by equation dxe divided by dt equals to minus ke x, where x is the amount of the drug in the body and ke is the elimination rate constant. So let's give a quick recap. In extravascular administration, absorption is crucial. There are four phases in plasma concentration time profile. The Tmax and Cmax values are key parameters. Absorption and elimination follows either first order or the zero order process depending on the drug and formulation. And that's all for today's video on the one compartment open model extravascular route. If this video helped you, make sure to hit that like button and share with this video with your pharmacy students and subscribe for more videos.